Welcome to the ITSP Magazine Podcast Network. You're listening to a new episode of the Leading Edge Discovery Podcast, where host and astronaut Charlie Camarda and his intriguing variety of guests share their visions for transforming the way we work, learn, and solve some of the most daunting challenges on Earth and throughout the solar system. Knowledge is power, now more than ever.
All right. Hello, my name is Charlie Camarda. I was an astronaut on the Space Shuttle Discovery return to flight mission following the Columbia accident. I will be your host today on Leading Edge Discovery podcast series, where we will be talking to experts from around the world in areas of science, technology, engineering, and math, but most importantly in research. We're focusing in aerospace and how we solve these critical problems, things that cause accidents like the Columbia disaster. And I am honored to have as our guest a world-renowned expert in hypersonics, the new CEO of a new organization called the Purdue Applied Research Institute, Dr. Mark Lewis. And I'm excited to talk to Dr. Lewis about a topic that's near and dear to my heart, but also one that I think is critical to the security of our nation. And he's going to talk about why that is so. Mark, thank you so much for coming and joining us in a podcast. And as I told you earlier, what we like to do is have our guests talk about what led them down this path of science, technology, and research. And you have an amazing, amazing background, many high-level positions in the government, professor emeritus at University of Maryland. Tell us how you got there.
Sure. First of all, it's always an honor to talk with you. And as a guy who studies hypersonics, I'm always in awe when I talk to someone who's actually flown at hypersonic speeds, which you did re-entering. So I feel like a poser a bit because I can theorize about it. You've actually done it. So thanks for having me in the panel. So wow, how did I get started in this path? I knew I wanted to do aerospace engineering from a very early age. I was a child of the 60s. I was born in 62. I was one of the kids who was glued to the television for every space flight, Gemini, Apollo. I remember watching Neil Armstrong walking on the moon, huddled, on a black and white TV, observing it. And it was just something that I wanted to do. I was always interested in airplanes as well. I was also one of those kids who, built a zillion model airplanes and flew model rockets. And by the way, much to the disappointment of my grandmother, who really wanted me to be a medical doctor, because, she wanted one of her grandkids to be a medical doctor. We all disappointed her. So I got to, I graduated high school, and I was always one of the nerdy STEM kids at high school, guilty as charged. And I did my undergraduate studies at MIT. And when I arrived at MIT,
not a bad school.
It's a technical, it's a trade school up in Boston. It was, for me, honestly, showing up at MIT was like arriving in heaven. So I'd gone to a high school in the Westchester County in New York. And, there were some really smart kids there, but not a lot of kids interested in science or technology. So again, there were a couple of us, we were kind of the nerd crowd at the time. That was back before being a nerd was cool. Now it's cool. Back then it wasn't. And then I show up at MIT and I'm surrounded by all these other kids who wanted to do science and technology and loved math. And it was like I had arrived. When I showed up at MIT, I knew pretty quickly I wanted to double major in two areas. I wanted to double in planetary science and in aeronautics and astronautics. And my original scheme when I was 18 years old was I was going to become a planetary scientist, but would have a background in the engineering. So when I, worked on projects, I'd kind of know the engineering wheels behind it. And then I had the opportunity to work in a planetary science laboratory and an aerospace engineering laboratory on campus. And I realized my thought processes were much more aligned with engineering than science. I love the science, but the idea of actually building things and creating things and solving problems, that was really what floated my boat. And I had among the many professors, I had these incredible professors at MIT. And my freshman year, the head of the MIT Space Systems Lab was this legendary professor named Renee Miller, who had started the MIT Space Systems Lab. And he used to have this saying, he said, engineers are just scientists who actually do things. And I love that. So long story short, I finished up my degrees at MIT. MIT liked to hire its own undergraduates into the graduate program. So I actually didn't apply anywhere else. I stayed on at MIT in the graduate program. Now, I actually started as a graduate student working in the MIT gas turbine laboratory, working on gas turbine engines, and specifically looking at flows on turbine blades. And those are, really fascinating technical problems. But at one point, I kind of had an epiphany, and that was, these gas turbine engines were really neat things, but we kind of knew how to build them. I mean, you could go to the gas turbine engine company and buy a gas turbine engine, and they work pretty well. In fact, they're about the most efficient machines on the planet. And around the same time, the United States began a program called the National Aerospace Plane Program, the NASP. It was the plan was to build a vehicle that was also given the name of the X-30. And there were two kind of elements to this. One was an airplane that could fly anywhere around the world in a couple of hours. And the other was a vehicle that could take off from a runway and fly all the way into space. And, with the hindsight of history, it was, a bridge much too far. I mean, we didn't know how to do that then. We still don't know how to do it today, but it was such a vision. And the president of the United States, Ronald Reagan, he went on national television. He announced this plan. And so all that was kind of brewing up. Yeah.
Mark,
yeah,
the Orient Express.
Right, yes.
We were going to go from the U.S. to Japan in, I don't know, 2 hours.
2 hours, 2 hours, yeah. Yeah, but it was this incredibly exciting vision. And, I signed up to be an aerospace engineer because I wanted to fly higher and fly faster. This was higher and faster. Anyway, so I was a graduate student. I finished up my master's in the gas turbine lab, and the timing was perfect. I started working on my Ph.D. in this area of hypersonics. And I smile because my Ph.D. advisor, my new Ph.D. advisor, was a brand new assistant professor by the name of Daniel Hastings. So Dan had been did his Ph.D. at MIT and then gone off to do National Lab and had just come back to MIT as a faculty member. And I'm smiling because when I went to work for him, all my friends and colleagues like, oh, he's the new professor. He's brand new. You don't even know if he's going to stick around here. What kind of an impact it's going to have. Well, Dan has also had this absolutely fabulous career. In fact, one of the best decisions I ever made was to go work for him as a graduate student. We remained lifelong friends. But so that really shaped my career. So I finished up in hypersonics. It was a wonderful time. I mean, we were funded by the Charles Stark Draper Laboratory. And they basically gave money to the MIT Aero Department, and the theme was, tell us what's important. They didn't give us a project.
Give a little shout out to the Charles Stark Draper Laboratory. Had a little something to do with Apollo.
They sure did. They sure did. And this really forward-leaning organization that came out of the MIT Aero Department. It was the Flight Instrumentation Laboratory. As you said, they got Apollo to the moon. Draper was this legendary professor at MIT. And so by the time I rolled along, there were some folks at the Draper Lab who knew they were really interested in supporting hypersonics. They wanted to work in this area, but they wanted to know what was important. I mean, what would they need to know in order to design control systems and navigation systems for these future hypersonic vehicles? So they basically gave the Air Department at MIT a grant and said, tell us what we need to worry about. It was like the best thing you could ever ask for. And there was a gentleman at the time by the name of Phil Hattis. He's still at Draper Labs. He was the one who funded this. So it was like the best opportunity for a PhD student. Yeah.
And you're talking about something that I think differentiates research and why we go into research, right? You talked about it. You talked about a little bit, a kid growing up in Westchester, New York, right? Yeah. I don't know. Oh, when I grew up in New York, I went to a good high school in, Archbishop Malloy High School. What was an engineer? Did you ever really have a good role model in high school that was a teacher in high school that actually understood what an engineer was even, right?
Yeah. So I'll give you the simple answer. No, I never did. And, this is going to sound terrible. I've spoken to a lot of high school teachers. And I always say, you can have an impact on that student. You can be a mentor to that student. I'm going to tell you, I didn't have that in high school. I hate to say it.
You're absolutely right, Mark, and that's one of the reasons why I try to get these programs at the high school level, teaching the educators how much fun engineering is and how creative it is.
Oh, absolutely. I think back to, I had some good teachers, but not really good math or science teachers. And, I'll tell you, so my senior year in high school, I was taking an AP chemistry class, which should have been, this eye-opening class. And I'll never forget, the teacher at the time, she's probably long gone from the face of the earth, but she was terrible. She had no idea what the science was all about. For her, chemistry was all about memorization. And you'd ask, and we had this group of, there were some really bright kids in the class. And we'd ask her, these probing questions. Don't just have us memorize the formulas, explain this to us. And she'd be furious at us. So then when I arrived at MIT, I've got these brilliant professors at the front of the room. And it was for me, it was, part of the joy of being in a place like that was I suddenly had people that, lecturing to me who, oh my gosh, I could learn so much from these folks. And they understood science and the scientific processes and inquiry. To me, it was just eye-opening. So
I love MIT, and I've done a lot of work with some professors there and the students there, and it's just an amazing, amazing place to get that interaction. And I know you talked about, gas turbine engines, right? And it just didn't float your boat because it wasn't what I call epic enough. You were looking for an unbelievable challenge. And so was I when I was at Langley. I'm a little bit older than you, a lot older than you. But it was the aerospace plane was the epic challenge.
Yeah. Oh, absolutely. Absolutely. So I finished my Ph.D. at MIT, and I knew I wanted to be a faculty member. And I said I had this phenomenal Ph.D. advisor, Dan Hastings, and he again, if I listed his career highlights, it is also been he's been absolutely amazing. But so, sit down, and we worked out the various places that I could go, to start a faculty career. And I wound up at the University of Maryland. And so 1988, I started there. And if you had asked me at the time what I wanted to do, what I would be doing for the rest of my life, I was going to be a professor for the rest of my life. That was my initial goal. I was also really fortunate because almost as soon as I got to Maryland, I got in contact with some really amazing people. There was a gentleman who had just arrived at NASA headquarters by the name of Isaiah Blankson. And Isaiah had come out of industry. He had been a PhD student at MIT in the previous generation. He knew the faculty members that I work with. He arrived at headquarters to champion hypersonics. And Isaiah, he passed away about a year and a half ago, very sadly. But one of these
what an amazing guy. Wave
riders and so much of what we're doing today in hypersonics you can trace to Isaiah's house. But he was so quiet and so unassuming, so in the background. But ideas like he was the guy who said, when we put something in the air, we want to have the same thing in the wind tunnel. It's the same thing we've done the analysis on, kind of analysis, ground test, flight test. He pioneered all of that. He pushed the idea of supporting academia, keeping this core group of university professors. So when the programs go up and down, Isaiah was like, we can't hit academia. We need to make sure academia has a steady flow. Anyway, so Isaiah actually got me started, and then worked with some great people at NASA Langley. Langley was my start. There's a fellow by the name of Ajay Kumar at Langley. He gave me Dick Barnwell. These folks got me started on a research career.
My roommate at Brooklyn Polytech, my classmate at Brooklyn Polytech was Peter Naffo, who was aerothermal fluids, right? He's unbelievable.
Oh, absolutely.
But the good thing about Langley, and the reason why we were able to do research, was because we actually had really sharp people at headquarters at that time that understood what research was and actually provided funding. Yeah,
I agree. Now, I will tell you, on a very sad note, I was just visiting with Langley a couple of weeks ago. It's a shadow of what it used to be.
I know.
And it was this incredible resource in the field.
I hope the administrator of NASA is listening to this and listens to this podcast, because NASA has not done research in probably over 35, 40 years, the level of applied research that we used to do in many areas. Yeah.
Oh,
but
absolutely.
We're going to talk about
All right, we'll get to that. So, so back to my career trajectory. So, I was on a very traditional academic path, assistant professor, associate professor, full professor. And then I got sidetracked. And the way I got sidetracked is I had the opportunity to serve on the Air Force's Scientific Advisory Board. And that was a classic example of it's not necessarily what you know, it's who you know, and timing is everything. So remember I mentioned my advisor, Dan Hastings. He had come in as the Air Force chief scientist. He'd spent 2 years as the chief scientist of the Air Force, which is, by the way, the most fun job in the Pentagon. I got to do it after Dan. So he had helped get me on the Air Force Scientific Advisory Board. They were doing studies of hypersonics. I got pulled into that. So long story short, this incredible time in the Scientific Advisory Board, and that was another eye-opening experience. The idea that I, as a professor of engineering, could work with a service like the Air Force and help them solve problems and apply my knowledge to these truly existential challenges that the service was facing. I just love that. A term on the Scientific Advisory Board it's typically 4 years. So they appoint you for 2 years, and if you don't screw up, you get another 2 years. You know, show up to the meetings, you get another 2 years. So I did it for 4 years. It's a part-time job, so I was still doing my professor job on full-time while I did the advisory board. As my time on the board was winding down, I won another lottery ticket. I had worked on a couple of studies that got the attention of the then Chief of Staff of the Air Force, General John Jumper. And so he asked me to come in as the next Air Force Chief Scientist. And as I said, that was like, it's the coolest job in the Pentagon. By tradition, the chiefs, yeah.
Did you ever get to interact with Joe Shabika?
Of course I did.
Oh, Joe what an amazing guy. Head of the Air Force Research Labs for a number of years. Very innovative. I'm going to love to have him on also. Yeah.
So Joe was the executive director, and he worked with probably my closest friend in the Air Force, retired Major General Kurt Bedke. So Kurt was the general officer running the lab. Joe was the civilian, the senior civilian. And then Mike Kolyasha was the chief technologist lab. We used to call them, the Miracle Three. I mean, it was such a team. And then I was the chief scientist at headquarters, and it was just this match made in heaven. I still try to get to see Joe whenever I'm out in Dayton, and Kurt Bedke. I see him almost once a week. I mean, it was just an amazing team. That's one of the things I learned in the Pentagon. There are some amazing people. That's
what was great as a NASA employee, to work on this joint program called the Aerospace Plane. And when you look at the number of contractors, aerospace contractors back then, we had like over a dozen big time aerospace contractors, hundreds of subcontractors, the national labs, the Air Force labs, the Navy, NASA labs. It was a phenomenal program. And another person I'm going to have on is Bart Bartholomew, who basically pulled that all together and ran an amazing program.
He did. And Bart is also someone I'm still in close contact with. And you're right. I mean, he had this teaming idea where we really got the companies working together as a national team. Instead of outwardly competing, they were all pooling their resources on this amazing project, which, as I said, it's funny. I look back at the NASA program, and it was incredibly ambitious. And with the hindsight of history, it's maybe a little bit too ambitious, but so many great things came out of it.
But it was well run, because right from the start, Tony DuPont sold that idea to DARPA, as you said in your presentation, 50K to Earth orbit, right?
Yeah.
And really, it took much more than that, but they realized that it wasn't state of the art, and they developed this amazing technology maturation program under Bart's leadership, where we almost worked in a badgeless society, sharing ideas among companies, industry, academia, and the government. It was amazing.
Yeah, absolutely. And I think I often talk about the aftermath of mass. And part of it was, I think, this collective realization that single stage to orbit, first time out of the barn, probably too much. But we can apply that technology in other ways, and especially the military missions. Mach 5, Mach 6, Mach 7, Mach 10 weapon systems using that same basic technology, supersonic combustion ramjets, maneuvering high lift over drag shapes, all those, the low-hanging fruit with the military applications. I smile when I say low-hanging fruit, because it's still incredibly challenging. But then, do Mach 5 before you do Mach 25. 5 times the speed of sound before you do 25 times the speed of sound. And so it really set the stage for so much that came afterwards, and the programs that we've got in the department today.
And for the general public, hypersonics means vehicles flying faster than
5 times the speed of sound.
5 times the speed of sound.
Yes.
Thank you.
Now, I'll still slip into professor mode. So it turns out there is no fixed scientific definition of hypersonics. There's a fixed definition of supersonic, faster than the speed of sound, because you can always, measure your speed relative to the local speed of sound. Hypersonics is a little bit fuzzier. So we generally say about 5 times the speed of sound. Some people would say it's less, some people would say it's more. But what's really important is when you're traveling at hypersonic speeds, a few key things start to happen. One is you get really hot. As you've got friction as the air is moving over your vehicle. It makes the surface of the vehicle very hot, and that's especially true of leading edges. So it starts driving the engineering design of your vehicle. You need to worry about, making it out of high temperature materials, handling the heat that vehicle is experiencing as it travels at those speeds. That's one thing that's really important. The other thing that's really important, any vehicle that's traveling at supersonic speeds generates a shock wave, a sudden jump in pressure and temperature in front of the vehicle, and then sometimes in other places in the vehicle. And the way I like to describe that to the layman is because the vehicle is flying faster than information can move through the air. So molecules of air don't know the vehicle is coming until, boom, it's right there. And so there's a sudden jump in conditions in pressure and temperature and density of the air as the vehicle is moving through the atmosphere. At hypersonic speeds, that shock wave gets pressed very, very close to the vehicle. And that dictates a lot of the features of the aerodynamics of the vehicle. So that's one of the other aspects that we include in hypersonics. And the other thing that's important about hypersonics is that traditional propulsion, air-breathing propulsion systems, engines that would work in the atmosphere, stop working at hypersonic speeds. Gas turbine engines only work up to about maybe 2.5, maybe pushing 3 times the speed of sound. Ramjets, much similar type of engine, they stop working at about 4.5, maybe up to 5 times the speed of sound. So if you're going to fly at hypersonic speeds in the atmosphere with some sort of jet propulsion, you need a different kind of engine. And coming back to that NASA program, we did a lot of work on what that engine would be like. And all that work is now captured in the military programs that you see that are addressing cruise missiles today.
No, exactly. So why is hypersonics so important right now, Mark? Because, the thing that worries me is that was my career for 22 years before I became an astronaut. And as you said, we had the lead over the Chinese. And NASA Langley had some amazing people. The Air Force had some amazing people. We were doing great things. We had the lead. All of a sudden, things change. And why is it important that this is such a critical technology for our national security?
Yeah.
We just learned, and it's blowing up in the news about China being ahead of us. Explain to the public why we should be worried about this.
Sure. So you're exactly right. It is a tremendous concern that we have peer competitors today who have basically surpassed what we were doing in the field. And they did it by reading our papers, sometimes legitimately, stealing information illegitimately. We essentially did our homework. And then it's painful for me to say this, but we made it easy for them because we took our foot off the gas. So let me give you a little bit about the history of the field, and then I can talk about why we are where we are today. The United States invented the field. The first human-made hypersonic object was a sounding rocket that got launched off of a captured V-2 rocket in 1948, something called Project Bumper. And they started launching it at the White Sands Missile Range. And after a few launches, they realized they needed a better location. So they moved the program to an island off of Florida, Cape Canaveral, which is how we wound up with Canaveral and then, Kennedy Space Center. Throughout the 1960s, we were flying at hypersonic speeds. The X-15 rocket plane was flying at hypersonic speeds. It was an amazing airplane that was rocket powered. It dropped off the wing of a B-52 bomber, lit off a rocket engine, accelerated to hypersonic speeds. The pilots on that program were legends. Neil Armstrong was one of the pilots. Scott Crossfield flew the X-15. Joe Engel, just it's amazing group of.
I think Joe Edwards. Did Joe Edwards fly that?
Joe Edwards, yeah. He flew it. You know, by the way, Scott Crossfield was one of my heroes growing up.
And remember, Crossfield and even Neil Armstrong both spoke at the NASA conferences that we used to have.
Yes, they did. Yes, they did. And you know, I just understand you were talking about, you know, careers and career paths. I consider myself amazingly fortunate because I grew up with all these heroes, and then in my career, I got to meet them and work with them. And I remember the first time Scott Crossfield called me up. I was a brand new university professor. And I've got Scott Crossfield calling me up, and I'm like, "Oh my God, I've got Scott Crossfield on the telephone," and just amazing. The first time I was on a telephone call with Neil Armstrong, and you know the 7-year-old inside me is saying, "Oh my God, I cannot believe I'm talking to Neil Armstrong." So in some ways, I feel bad for the next generation because they haven't quite had that. So anyway, back to why hypersonics is so important. So it was a field that we invented. We developed the National Aerospace Plane, and then we took our foot off the gas. We did national hand-wringing. Do we need to invest? Do we need to go fast? When we had programs that failed for reasons unrelated to technology, we canceled them anyway. When we had programs that were successful, we canceled them. You know, NASA flew the X-43 vehicle. It was the first scramjet, you know, jet-powered, hypersonic, high-lift configuration. It flew at 7 times the speed of sound, then it flew at 10 times the speed of sound, and after we did that, we canceled the program. The Air Force had a program called X-51, again, scramjet-powered. It worked beautifully and flew once in 2010, flew a second time, totally successful in 2013. What did the Air Force do? Ended the program. It's mind-boggling. Meanwhile, we were producing papers saying hypersonics has a lot of military utility. And I'll get to that in a moment. And so other people read this. China read it. Russia read it. So they developed their programs and got ahead of us. So let me step back and talk about why hypersonics is so important. What is hypersonics? It's not just speed. We've had high-speed things since the 1950s. You know, Charlie, you flew at hypersonic speeds in the space shuttle. Today, when we talk about hypersonics, it's really shorthand. It's shorthand for the combination of speed and maneuverability and the particular altitudes at which you can operate, right? So a hypersonic vehicle, we use that as shorthand for something that goes really fast, but can maneuver. It can bank, it can dive, it can change course, and it can fly at a particular altitude that makes it difficult to detect either from the ground using radar systems or from space looking down at the Earth. So now imagine I apply that technology to a missile. I have a cruise missile that goes really, really fast, that can bank and maneuver, so I don't know where it's going to go. And that's particularly hard to see because of the altitude at which it's flying. What does that mean? It means I've got a weapon that can penetrate into enemy airspace that is very difficult to stop. Not impossible to stop, but really difficult to stop. And so you step back and say, why wouldn't you want that if you're military? Well, the answer is obviously you want that. And countries like Russia and China have invested heavily. Think about what the Chinese can do with hypersonic weapons. So what are the Chinese afraid of? We know the Chinese are planning to take Taiwan. If they can do it with soft power, they will. But they're also gearing up to take it with military power. And they've made no bones about that. They've freely advertised it. They've announced it. They've said, be prepared, 2027, that's where we're going to take Taiwan. Okay, so what are the Chinese worried about? They worry about our Air Force, and they worry about our Navy. That's what they're worried about. We know they're ramping up. I mean, they're investing heavily in their Navy. They're investing heavily in their Air Force. Okay, but still, they're not going to go toe-to-toe with the U.S. Navy. They can build all these nice, shiny ships, but it's not just the ships. It's the crews and the experience. They're not going to go toe-to-toe with the U.S. Air Force. One-on-one, I'm sorry, we will beat them every time. So how do they win? They will win by keeping the U.S. Air Force from ever getting into the air. It means you attack the air bases. You created the airfield so our airplanes can't take off. How do you beat the U.S. Navy? You beat the U.S. Navy by scaring the Navy out of the area of regard, making it clear to the Navy, you know, you sell your ship in there, we'll hit it with a missile, we'll sink your carrier. And as a stepping aside, that would be an incredible calamity. You know, if we lost an aircraft carrier is a $14 billion ship with about $10 billion worth of airplanes and 4,000 to 5,000 human beings on board. So the Chinese have figured this out, and that's why they've invested heavily.
It's a city, right? And so
It is a city.
These are all the reasons, and they are ahead of us, right?
They are.
But
they've already deployed.
But now we have the Ukraine. We have the conflict in Ukraine, and all of a sudden they shoot down a hypersonic weapon that was aimed at them from Russia, and all of a sudden now people are thinking, hey, we don't have to worry about these things. Why isn't that true, Mark?
So people have asked me about, the Russians have been flying their hypersonic weapons in Ukraine. By the way, that makes no sense. I mean, they're going against targets that don't require hypersonic weapons. So this is just the Russians showing off what they've got. And they've been shot down. And the reason they've been shot down is the Russians build really crappy weapons, right? We know the way they design these weapons. We know the way they operate. And they basically, without going into too many details, they bleed off most of their energy, most of their speed. And so those weapons wind up being incredibly vulnerable. So they're pretty useless. And I will tell you, I never worry too much about the Russian programs. The Russians have been mostly bluster. It's the Chinese programs that I worry about. And the Chinese, I think, have engaged in a fair amount of watch my left hand, because my right hand is really doing the important thing. And I'll kind of come back to, hypersonics. One of the issues we face with hypersonics is that people think hypersonics is just one thing. They think it's, large, expensive maneuvering missiles. It's not. It is a wide range of capabilities. It's medium-range maneuvering missiles. It's air-launched things. It's cruise missiles. It's rocket-boosted missiles. It's a wide range of capabilities. The Chinese have been very vocal and have basically gone out of their way to show us some of the things they're doing in the large scale. And yet it's the smaller things that I worry about most. It's the tactical weapons. It's things that, fly off of from under the wing of an airplane, or can be launched from a small mobile launcher, or can be launched from the surface of a ship, or maybe from a submarine. That's the thing that scares me the most, because they're lower cost. That means that you can build more of them. And they have some really scary implications, as I mentioned, impacting the operations of an air base, impacting the operations of the Navy. So
they have, you talk about we've got up to Mach 10 in some of our tests, but that was for like how many seconds? 20 seconds or
not even. So NASA did. So the NASA X-43 actually was the first to do everything in Mach 10. They did it for 11 seconds. X-51 in 2013 did Mach 5 for about 210 seconds. We've since surpassed that. For programs including the DARPA programs, Tactical Boost Glide and Hawk have surpassed both of those. But we've also done conventional. Yeah.
No, go ahead.
Oh, we've also done the conventional prompt strike program, especially the Navy program. They've done hypersonics for much longer. It's a bigger weapon. It's a bigger system, but they've done hypersonics essentially across the Pacific for minutes and much higher Mach numbers, and very successful.
But now the Chinese actually have operational capabilities.
Correct. Yes, and that's the big difference. So we've got a lot of programs. I want to step back. So, talk a little bit about my career. I did the Air Force for 4 years, went back to the university, was at the Institute for Defense Analyses, then wound up back in the Pentagon, first as the Director of Defense Research and Engineering, overseeing modernization. And then I finished up as acting as the Deputy Undersecretary for Research and Engineering. And that was a really wonderful time in the Pentagon, from the standpoint that we had a Secretary of Defense, Mark Esper, one of my heroes, and a Deputy Secretary, Dave Norquist. They understood the importance of hypersonics. We had all the service secretaries lined up. They all understood the importance of hypersonics, but all the service chiefs. So they actually put a huge investment in hypersonics. And it was the recognition that we had the China threat. And every meeting I had with then Secretary Esper, it always started out with, what are the Chinese doing? And the simple answer was, they had already deployed systems. So we put all these programs into place, and some of them were, well-conceived programs, but we haven't deployed. There's still R&D programs. And even worse, our programs right now aren't talking about delivering hypersonics in sufficient numbers. And here's what I mean by that. So if you look at most of the programs, they're talking about a handful of weapons. Yeah, we'll have a couple of hypersonic missiles on a truck somewhere or on a ship or, on an airbase somewhere. That's not going to scare anyone. Whenever we did war games with hypersonic weapons involved, we learned two important facts. Fact number one, whenever we, the United States, went up against an opponent that had a hypersonic capability, if we didn't have that capability, we lost, period. End of sentence. So that's one of the reasons why we absolutely needed it. The second thing we discovered, when we did war games where we were going up against an opponent that had hypersonics and we had hypersonics, then it came down to who had the deepest magazine, or who had the most weapons. A little bit of a war of attrition. They're hitting us, we're hitting them. So you need to have a lot of these. So if they got 1,000 and we've got 10, it doesn't do us a lot of good. So what we ramped up, and we put this program into place, which we called the Hypersonic Acceleration Plan. And yeah, we had a lot of people making fun of us. Yeah, hypersonic acceleration. But the idea was not just to develop a capability, but you need to do it at scale. You need to be thinking about delivering hundreds, thousands of systems. That's not just buying the weapons, by the way. It's having the whole supply chain, the whole production line. You need to have industry thinking in terms of how do I manufacture? How do I not just make 5, engines a year? How do I make 50 engines a year, 100 engines a year? Not just how do I make a few pieces of a high temperature material for a couple of sharp leading edges. How do I go to production where I'm producing 50, 100, 1,000 at some point, sharp leading edges that can handle the heat load? And that's the key, and that's where we are truly lacking. It's something that this nation has to focus on.
One of the things that troubles me the most is because I'm very passionate about education, as are you, Mark. And I look at the U.S. education system and how far behind we are and how much work we need to do really in producing the numbers of students that have this deep understanding, and when we look at the Chinese, they're probably orders of magnitudes more advanced degreed students in China than in the U.S. They're outpacing us by probably an order of magnitude in the number of new resources like wind tunnels, hypersonic wind tunnels, test facilities, things like that. The other thing that's important is, and what was the beauty about research and having national labs in the Air Force and at NASA, was the mentorship that these students needed to have coming out with a Ph.D., solving these highly coupled interdisciplinary problems as a transdisciplinary team in order to create and solve and understand why these systems and subsystems fail and how to make them survive, how to make them work.
Yeah. So Charlie, you've hit a topic which is absolutely near and dear to my heart. So you're exactly right. I mean, I worry a lot about the workforce. Now, I'll give you a good news, bad news story. So as a professor, I never had any trouble attracting the best and the brightest students to work in hypersonics. I mean, it's the most, in my opinion, it's the most exciting area of aerospace engineering. It's things that move really, really fast, really, really high, that have these, it has this incredibly, it could have incredible impact in so many different areas. I mean, imagine if we could build hypersonic airplanes that could take you anywhere in the world in 2 hours. Imagine if we could build hypersonic launch vehicles that really could get from the ground all the way up to orbit with airplane-like operations instead of rocket operations. This to me is amazing. So I never had any trouble attracting students.
And it's not only the students, right? And this is what troubles me about NASA. Even when I retired, our product development is still like waterfall, maybe V diagram, and it's not the way. We need to use set-based. We need to use set-based design techniques, advanced techniques for rapidly producing, rapidly learning.
Yes.
And the government is these established hierarchical bureaucracies. How do we solve this?
Oh gosh. So, I'll tell you I'll tell you the following experience. So a number of years ago, I was on a panel that was asked to review NASA Langley's hypersonics portfolio. And we were reviewing it essentially to the then center director, but then for him to report up the chain to the then administrator. I think Charlie Bolden was administrator at the time. So we spent 2 days with the hypersonics folks at NASA Langley. And I want to emphasize, Langley used to be the place for fundamental hypersonic science. I mean, anyone who worked in, computation and analysis, you worked at NASA Langley. Anyway, what we saw was the shadow of the former program. So much so that when we did our outbriefing to the center director, we said, I remember this very clearly. We said, you asked us to evaluate the quality of this S&T portfolio. You have so under-resourced this portfolio that we don't think it's fair to them for us to evaluate them. This is not fair. And what we really will tell you is you need to put more resources into it. Now, here's one of the,
You want to know something? That worries me tremendously because, we solved some major problems after the Columbia accident investigation.
Yes.
If we didn't have those research centers, we wouldn't have been able to solve those problems. And Johnson Space Flight Center would never have been able to do that. But the NASA administrators don't understand this.
It's really painful. Now, here's the one that really got me. And I remember as part of this review, we were talking about scientists and engineers at NASA being able just to discover. So one of the individuals that I got to meet, another one of my heroes that I got to meet as a young faculty member, was a gentleman named Dick Whitcomb. Whitcomb, legendary aerospace engineer. He invented not one, not two, 3 major aerospace developments.
And not only Draper Labs was great, but it was Whitcomb's Lunar Orbit Rendezvous that really got us to.
So Whitcomb, he came up with the winglets.
No. I'm sorry.
You think of John Humboldt.
That's Humboldt. That's Humboldt. I'm sorry.
However,
Dick Whitcomb, Coke area rule, winglets,
and supercritical wings, but he and Humboldt were best buds, by the way. And I got to meet them because the guy who hired me, the department chair who hired me at the University of Maryland as a fresh out PhD student, was a fellow named Al Gessow. He'd been at Langley for many years. He was Mr. Rotorcraft, and he and Whitcomb and Humboldt, they were all buds. So I got to get on the tail end of that. By the way, as an aside, the guy who hired me as a faculty member at Maryland, Al Gessow, he had a picture in his office when he first started at Langley in the late 1940s, and there's Orville Wright shaking his hand. I was like, oh my God, the fellow who hired me into my first real job knew one of the Wright brothers. This to me was always my
these guys were amazing, amazing experimentalists. Dick Whitcomb was an amazing experimentalist. Yeah. Always in the wind tunnel, and that's how he was able to innovate. And it was this clash between the theorists and the experimentalists that made NASA Langley so great, and the realization that you needed both.
But the other thing that made it great and that made a guy like Dick Whitcomb so successful was he could come up with an idea, such as the area rule. And then he could walk into the machine shop and tell the machinist, I need a model that looks like this. And then he could take that model and he could walk it into the wind tunnel and say, put this in the wind tunnel, I want to measure the properties. That doesn't exist today. There's no process like that.
Was a totally different culture, and that's what I call the research culture. And when you read the historians, Schultz's book on Langley and how these research centers started, that's what we need to recultivate at these organizations.
Yes. Now today, if a researcher at a place like Langley wants to do that, they walk into the machine shop and say, I need a model. What program are you charging to? And I need some wind tunnel time. Oh, what program are you charging your wind tunnel time to?
Exactly. Or even worse, some program manager who has very little technical experience is directing that person. And there's layers of people you have to convince that this is a great idea because they don't really understand it. Exactly.
And, back to your point about mentorship. I mean, you look at the great days of NASA Langley, and you just had this legacy of a longtime folks who work in the field. You mentioned Peter Naffo, for example. I remember when Peter was a young guy, and then, he was one of the graybeards at Langley. My most recent trip, I'm not seeing that. They're not bringing in the refresh. There's no way, we're not leveraging that investment.
We're not getting the best and the brightest. And I just read this recently. I read a book about Elon Musk and these other companies. These kids want to do something.
Yes.
And what was beautiful about being a researcher, you just like you said with Whitcomb, if you had a good idea, you had technical managers that would give you the go ahead and you could go ahead and do it.
Yeah.
And we just don't have that. Everything is governed by a program. It has a specific purpose. It's no more research. You have and you have to bookkeep every hour that you work. That is not a psychologically safe, good research environment to test ideas and to be innovative.
I agree. And I hate to say it because the NASA aeronautics portfolio goes so near and dear to my heart. And yet I look at that portfolio and I just want to scream. I mean, I don't see the excitement. I don't see the innovation.
And you want to know something? Even though it's the lowest budget element of what they are doing, believe it or not, the most creative and innovative work. And that's sad to say.
Yeah, it is. It's 3% of the NASA budget. And they're always fighting for their existence. But we for many years we battled to keep NASA in the hypersonics area, and it's almost becoming a losing battle. Now, let me give you an example, by the way, of why that's so important. So I'll tell you an interesting story that happened during the X-51 program. Remember, that was the Air Force's program to build a missile class hypersonic vehicle. It flew between 2010 and 2013. So we're gearing up for that program, and the key technology of X-51 was the engine, the supersonic combustion ramjet type of engine that we envision as being the key engine to power jet power through the atmosphere at hypersonic speeds. So we're going to test it at an Air Force wind tunnel. And that wind tunnel wasn't available because it was being refurbished. It was down for maintenance. So we, the Air Force, went to NASA and said, can we use your wind tunnel? It was the Langley 8-foot tunnel.
That's where I grew up. That was my branch.
And the folks at Langley they did a heroic effort. They got the tunnel ready. They had to redesign a nozzle in record time. They got the tunnel ready. We were able to test the engine. It's this beautiful story. The engine was successful. The program was successful. But if you step back and say what happened there, what actually happened, it wasn't just the tunnel. It was all the incredibly smart folks who had worked on NASA's own program, the X-43. And because they were connected to the tunnel, we got not just the tunnel, we got all these really smart people with all this experience now working on X-51. And I remember when we did the first flight of X-51, 2010, I was in the control room out at Edwards, and sitting right beside me was Randy Volan. Randy had been the chief engineer on the X-43. So I had the guy who was running X-43 sitting next to me for X-51. It was this, amazing example of, government agencies working together. If you don't keep that legacy going, it's not just NASA that suffers, it's the entire government.
Mark, we've talked a lot about problems, how we got to this place. What I love about you, Mark, is because you have this amazing energy, you have this passion, and you have this expertise, and you are in a beautiful position. Because this is going to take a conductor that has this amazing orchestra, the DoD, that loves to work in silos. You have the ability to convince people at not only headquarters, in the Pentagon and in the government, why this is so critical. And you need to come up with a plan to pull it all together from the grassroots, getting the students, mentoring the students, and coalescing to get this research back ahead of the Chinese. And I know you're the guy that can do it. I know you have a plan.
Yeah.
Do you want to share? Do you want to share it with us?
Yeah. Wow. No pressure. So obviously it's an area that, as you can tell, you're exactly right, near and dear to my heart. And if you roll back, when I first started as Air Force Chief Scientist, so that was 2004. I was pushing the Air Force really hard to invest in this area. And I should explain, the Chief Scientist job, so you don't directly control any money, you don't have lots of people working for you, you're simply providing advice. And the old saying, a prophet in his own land is often underappreciated. I had a couple of really strong allies in that. One is a very dear friend, Dick Hallion. Dick is maybe the world's foremost aviation historian. And the two of us have put together some plans, some ideas, and how we can get the Air Force to invest. They did finally listen, and I think it was a combination of factors. One was in 2016, I was involved in a study that looked at what our peer competitors were doing. and the Russians, but especially the Chinese. And the intelligence community had been sounding alarm bells, but 2016 we put it all together and we said, basically, holy crap! This is the Chinese have done a national level investment, and we pitched it. And at the time, the acting Secretary of the Air Force was Lisa Disbrow, and Mark Welsh was the Chief of Staff, and the two of them got it. They understood why it was so important. Lisa convened a 5-hour meeting of the entire air staff of the U.S. Air Force in May of 2016, and she basically charged the air staff, like, this is important. We need to address this. And General Wilson, Seventy Wilson at the time, who was ultimately became the Vice Chief of Staff of the Air Force, the #2 General in the Air Force, basically took this on. And so the Air Force was off and running. So that was kind of the good news. The Navy also took it very seriously. The Army took it very seriously. So as I mentioned, in the previous administration, we got significant funding invested in this area. And one of the reasons that I was brought into the Pentagon as a DDR&E was to kind of help oversee this. We had we had a team, we had a principal director for hypersonics, kind of doing this overall roadmap. So where are we today? Well, sometimes it's 2 steps forward, 1 step back. So if I do the assessment today, I think we still have a sense in the Pentagon and across the government that hypersonics is important. I talk to congressmen, I talk to senators. No one ever disputes this. And you've got some members of Congress who really stepped up as champions in this area. Congressman Lamborn, for example, has been a strong champion of hypersonics. Representative Banks from Indiana is, the two of them are co-chairing a hypersonics caucus that is addressing this very issue. I don't think I've ever spoken to a member of Congress who, when I explained to them what we were facing, why this was important, didn't get it and didn't support it. If I look through the Pentagon leadership, again, the folks who are now in the office that I was in, Undersecretary Hsu, Deputy Undersecretary Dave Honey, they all get this. What I worry about, though, is that whereas we were messaging on our team that hypersonics was absolutely a top priority, our #1 or #2 priority across the entire department, I hear that message getting diluted. I hear people in the Pentagon saying, yeah, hypersonics is important, so are other things. AI is important, cyber is important. Yeah, I get it, they're important, but you gotta have priorities and you gotta communicate those priorities. When I go through the list of DoD priorities, the priorities are pretty straightforward. Microelectronics is high up there, no question about that. Hypersonics also has to be up there. And the reason I say that is, I'll come back to I mentioned earlier, wargame experience. Every time we did a wargame with hypersonics, if we didn't have it, we lost. If we had it, but we didn't have it enough numbers, we lost. So it is absolutely critical. So what do we need to do? I actually think the most important player in this is the United States Air Force. Because, Navy mission is important, Army mission is important, but it's really the Air Force mission because, where does hypersonics play in best? We say on the air staff, the Air Force mission is to knock down the door. Right? The Air Force is there first. It's air power. It's the application of air power. So if I can have hypersonic tactical systems, weapons that I put in bomb bays, weapons that I put under the wings of airplanes, that can have a decisive, can be a decisive factor in any future combat. Strong deterrent factor, by the way. The best weapon is the weapon that I never use. So let's, get that right out there. We don't want to use our weapons, but if we have to, we want to be able to kick down the door. Hypersonics lets you do that. I like the idea of hypersonic systems that, for example, are integrated with existing aircraft. I want hypersonic air-breathing weapons underneath our 4th-generation fighters because that gets them into a 5th-generation fight. So, my F-15s, my F-18s that are getting old, they're getting a bit long in the tooth, still amazing platforms, but they're not going to do well in a 6th-generation fight against stealth aircraft. So suddenly, if I can fit them with hypersonic weapons, they're back in the fight, and I can deliver it in numbers that count. All right, so what are the most important things to do this? A couple of steps. 1, we need the workforce. So back to your point. 2, we need test infrastructure. This is critical. You mentioned earlier that China is investing heavily in wind tunnels. We were busy shutting down wind tunnels. We need to reinvest. And I'm very proud to say part of my new job at Purdue, we're building wind tunnels. We're building world-class wind tunnels. So that's something we got to do. another thing we need to do. We need to get the cost down. There is this sense that hypersonic systems will always be expensive. No, that's not true. And by the way, the Russians and the Chinese seem to be able to build these things at reasonable cost. But if I dissect a hypersonic weapon, there isn't an obvious reason for that weapon to cost a lot more than a more conventional weapon. I'll give you the example. Think about a hypersonic cruise missile, right? I've got a jet engine, but that jet engine is a very simple engine. A supersonic combustion ramjet is, in principle, about the simplest engine you could ever imagine. It's just an empty duct. It's a tube. Air comes in the front, right?
In terms of moving parts, yeah.
Moving parts, right. Compare that to, a subsonic cruise missile. It's got a turbine engine. It's got compressors and turbines and all this complicated crap. So the hypersonic weapon shouldn't be that much more expensive. Yeah, it's difficult to manufacture, so I need to get my manufacturing costs down. It's got some exotic materials because it's got to handle the heat. I got to get the cost of those materials down. But there are people who think, hypersonics, that's like 10 times more expensive. No, wrong. Hypersonics isn't going to be more expensive if we do it right. And that's where we need to focus.
Let me jump in there. I mean, I know what you're saying. I was a thermal structures guy. And so having these systems survive, and you talked about the cooling, these are highly coupled transdisciplinary problems that we have to train researchers on to do them smartly. It's not just a more advanced material. How do you cool it? How do you make sure it survives? Yada, yada, yada. How do we mentor these kids to do that? And it's gonna take a while. But continue with your plan, Mark. I'm loving it.
So by the way, I think one of the many things that I love about hypersonics is, just as you say, it is the most interdisciplinary field that I can think of. All right? A hypersonic vehicle, by its very nature, has to be designed so that all of the aerodynamics, all the structure, all the materials, all the propulsion are fully coupled. I'll give you an example. For an air-breathing system that uses oxygen from the atmosphere, the whole front of the vehicle is the inlet of the engine. The whole back of the vehicle is the nozzle of the engine. So you can't think in terms of a separate engine. The whole thing is a flying engine, or sometimes I'd say it's a flying self-propelled fuel tank. We had tended, when we train students, when we educate students, we tend to pigeonhole them. We tend to put them in stovepipes. You're a propulsion engineer. You're a structures engineer. Hypersonics has to break down those barriers. And I'm proud to say it's something that we're doing. If you look at the university programs now, driven in part by the Department of Defense, you're seeing more and more programs that are interdisciplinary. I'll highlight one program. The department set up something called the Joint Hypersonic Transition Office with a lot of support from Congress. They are funding a university consortium. This consortium now has over 100 universities. And the beautiful thing about this consortium is it has brought in addition to the usual suspects, the fluids people, the propulsion people. You've got material scientists at universities. You've got guidance, navigation, control people. You've got manufacturing experts. It's showing us how this has to be done.
Not for nothing, Mark, but I got to spend time when I was at NASA. They let me have a detail at NYU at my old school, Brooklyn Poly. It's now the Tandon School of Engineering at NYU. And what I learned from that 2-year experience was that universities could be more bureaucratic, more hierarchical, and more siloed than even NASA was at that.
Yes. Oh, you're right. Look, when I first showed up at the Pentagon, people would say, how do you deal with the Pentagon bureaucracy? I left myself silly. I said, this is nothing compared to a university. And so you're absolutely right. But we're seeing really strong efforts to break down those silos. The job that I just started at Purdue, one of the motivations there was create an organization that's affiliated with the university, but moves quickly, is fast, is light, is nimble, can bring researchers on board quickly, can respond to government interests quickly, and do unique contracting, all those things. So universities are getting the message.
And we have this consortium. I know I spoke to some of my friends at Texas A&M and these other universities that, but there's got to be a conductor that orchestrates this and integrates this to get the most bang for the buck, to get the most learning for the least amount of dollars, so we're not wasting money. And by the way, not only are this typically do things siloed, now you have classified programs, and to be able to transfer classified material not even within one program, let alone several programs, we don't have enough subject matter experts to spread that knowledge across all these programs. That's almost the epic challenge within the epic challenge. But you're the guy that could solve it, Mark. I believe
don't know. Yeah.
you are the guy that could do it. If anybody could do it, you could do it.
I don't know if I'm worthy, but you're right. I mean, there are many elements of this, and making sure we've got the right expertise is key. So I'll tell you one of the fun things that I discovered. So I show up back in the Pentagon in 2019, and the fun thing that made me really proud to have been an educator was I saw so many of our mid-career and senior leaders were people I had worked with at the university, former students, former undergraduates, former graduate students, former colleagues. So there are the smart, talented people in the government. That's kind of the good news. The bad news is they're not always appreciated. And, I'm sure you've seen this also. I mean, there are times when there's almost a disdain in parts of government for technical qualifications and technical talent. And I would encounter that. The bean counters who are really good at what they do. They're really good at counting dollars, but then try to make technical decisions, and they're not at all qualified to make those technical decisions.
You're touching something that's near and dear to my heart, because I've researched a lot about how accidents happen and how these cultures get so dysfunctional, especially at NASA. And it's amazing, as a researcher from Langley, when I went into the astronaut office, what was amazing to me was during my interview period, the center director basically said, "Why don't you leave Langley that he called it a library?" He said, "Why don't you leave that library and come to work for a real organization? We build hardware." Had no appreciation for the research, did not know even when they had people that could have prevented those accidents at the research centers, didn't even contact them. That's how bad it was.
Yeah, so I see that too. I mean, there's kind of a lack of recognition of the importance of the S&T investments that we as a nation make. And I was actually just talking to a good friend in the Pentagon earlier today on this very issue. And, you trace back, you look, for example, it's look at my iPhone. Almost every piece of the technology in this iPhone can be traced back to basic science technology investments that are made by the U.S. government. You look at everyone talks about artificial intelligence today and how the commercial industry has gone beyond what the government is doing. Great, but look at how they did that. It was from fundamental research investments that were made by the U.S. government.
Don't get me started with Burt Rutan jumping up and down and said scale composites 1, NASA 0. They didn't know what composites were if it wasn't for the U.S. Air Force labs at Wright-Patt and NASA Langley.
Exactly. Look, even SpaceX. So where did the original investments for SpaceX come from? The Falcon 1 vehicle came out of a DARPA program. So people tend to underplay that. And, what I'm scared about is I'm hearing more and more this notion of, but investing in basic research is all fine and good. But we need to actually build stuff. Well, you know what? If you don't invest in the basic research, you won't have any stuff to build. You won't have any future things to build.
Mark, let me tell you something. I could talk to you for days,
Yeah.
and I hope I get the chance to visit you at Purdue. I'd love to talk to your students, and I'd love to watch what's happening. But we're going to have to close because it's almost an hour, and we could have another session. I'd love to have another session with you. Going to have another session with Bart Bartholomew. I think the country needs to hear from even some of these old timers like me, and even older timers like Bart, because it's almost like we need a program like a NAS program to bring all the different elements from all the different agencies working together as one integrated team to share that knowledge, because we need to accelerate the knowledge. We need to accelerate the students that understanding these knowledge. Oh, by the way, they have to be U.S. citizens, and we need more of them. So any way at all that I can help you and the team, Mark, you have a daunting challenge in front of you. What would you like to leave the audience? Hopefully on a positive note?
So really positive note. Look, I'll leave the audience with and I'll especially address it for the young folks who might be listening to this. I know of no more endeavor in engineering that is as exciting as hypersonic flight. I mean, the thought of hurtling through the atmosphere at speeds that are greater than a mile per second, that's what hypersonics is. The implications that can have to the military, to the civilian sector, the role that it plays. And we didn't even talk about the space applications. That's a whole other aspect of hypersonic flight that you experience firsthand. Anytime a vehicle enters the atmosphere of Mars or Jupiter, it's a hypersonic vehicle. This is an incredibly exciting field. We need the best and the brightest. We've got existential threats that we're facing, but we've also got these incredible opportunities opening up ahead of us. And there are some really brilliant minds that we can bring to bear in this area.
Mark, thank you so much. I mean, we're so lucky to have you. You're such a busy guy. Thank you for sharing the time with us today. And anything we could do to help, we're gonna post. If you have a website, if you have a place for students and researchers to contact you at the Purdue Applied Research Institute, we're gonna host it on the podcast. All those connections, so that you could share your vision and inspire more people like me and other future explorers. Mark, thank you so much.
Charlie, always a pleasure. I love talking to you. I'll be back anytime you ask.
Thank you so much.
We hope you enjoyed this episode of the Leading Edge Discovery Podcast with Charlie Camarda, part of the ITSP Magazine Podcast Network. If you learned something new and this conversation made you think, then share this channel and itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey.